Okay, goal of this lecture is to work some example problems on the node voltage method. So we'll start out with a simple one where we just have some current sources. Just kind of making this up as I go along. We'll label these values. Okay, try to use different numbers for everything so that as I write through the equations, you can follow what number goes with what. And so the first thing that we want to do is we want to identify the nodes. So we have one here, 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 and at the bottom. No node in the upper right corner because that 3 ohm resistor is just connected to the top and bottom node. Now I'll identify a reference node and I'll choose that to be here at the bottom, and I'll label the remaining node voltages. So V1 basically represents the voltage between this node 1 and ground, V2 the voltage between this node and ground, and V3 the voltage between its node and ground. Alright, so writing the first equation at node V1, we have minus 5 because it's entering the node, and then we have plus V1 minus V2 over 1 is 0. For the second node, we have, if we were to draw a circle around that, we see it's got 3 branches. Once again, assuming all the currents through resistors leave the node, we have V2 minus V1 over 1 plus V2 minus V3 over 2 plus V2 minus 0, and we will not put the 0 over 4 is equal to 0. And then finally at V3, we have V3 minus V2 over 2 plus V3 over 3, because that would be V3 minus 0, and then plus 10 equals 0. Positive because it's leaving the node. Alright, so we'll simplify some equations and collect like terms. So for equation 1, I get V1 minus V2 is 5. For equation 2, I get minus V1 plus 3 halves plus 1/4. So what would that be? If I found a common denominator of 4, that would be 4 plus 2 plus 1. So 7 over 4 V2, and then minus 1/2 V3 equals 0. Okay, I think that's right. We have plus 1 plus 1/2 plus 1/4 and minus 1/2. That looks good. Okay, and then my third equation, I have minus 1/2 V2 plus 3/6 and 2/6 is 5/6 V3 is equal to minus 10. Okay, I believe barring any math error, that looks good. Okay, this is fairly straightforward to solve by substitution. Or you could use a matrix method. So if we use a matrix method, we would use Kramer's rule. So the first thing that we do is we find the determinant of the coefficients, and then we would use Kramer's rule to solve for each unknown. Rather than that, I'll just use substitution. So V1 is 5 plus V2 and 5/6 V3 is minus 10 plus 1/2 V2. So V3 is, if you invert some things, minus 12 plus 3/5 V2, I think. So this becomes 6/5 times 10, which is 12. 6/5 times 1/2 is 6/10, which is 3/5. Alright, so now I'm going to take both of these, this one and this one, and I'm going to substitute into equation 2 and solve for V3. So from equation 2, so into equation 2, and I'm working this out all the way because I was surprised last fall how many students struggle to actually get an answer. My focus in this class is always how you write the correct node voltage method equations, but really had students struggling to solve 3 equations, 3 unknowns. If you have any familiarity with MATLAB, you can do this in MATLAB really easily using Kramer's rules. Very easy to take a determinant in MATLAB. The other option is if you Google Wolfram Alpha simultaneous equations or systems of equations, there's an applet that'll come up that's online, and it'll solve these fairly easily as well. Anyway, let's continue. So substituting into equation 2, first for V1, I have minus 5 plus V2 plus 7/4 V2, minus 1/2, and substituting for V3, minus 12 plus 3/5 V2. Okay, let's check that. This is V1. This should be V3 minus 1/2 and negative sign. Okay, we look good. So minus 5 minus V2 plus 7/4 V2 minus plus 6 minus 3/10 V2. So we'll switch to decimals. Let's see, 3/4 is, so this is 1 minus, or this is minus 1 plus 1.75, so out of that we get 0.75 V2 minus 0.3 V2, and I got a minus 5 and a plus 6, so that's a plus 1. So 0.45 V2 is minus 1, so V2 is minus 1 over 0.45. So let's see if we can find a calculator. I have one somewhere. Where is my calculator? Maybe not. May not have that app active right now. I am not seeing it. So we'll just go back. We'll leave that as minus 1 over 0.45. I think that's actually 2.2 if you divide that out. So we'll put an approximate. Okay, that makes V1 5 plus V2, which will make that approximately 2.8, and it makes V3 minus 12 plus 0.6 times minus 2.2, which is about minus 12 minus 1.32, so that is minus 13.2, assuming I didn't make any math errors. Alright, now let's keep these, and because I was doing this in my head, this may not work out perfectly, but let's now see what you do with those. So we come up here to V1, and let me change colors. V1 here is going to be, what did we say, minus 2.2? No, 2.8. So this is 2.8 volts. This is minus 2.2. And then this one we said was minus 13.2. Okay, so what that means is that this voltage is minus 2.2 volts, and this current is V over R, so it's minus 2.2 over 4. And you notice I'm just keeping my negative signs. This voltage, plus minus, is 2.8 minus a minus 2.2. So this is 5 volts, which I actually knew that anyway, because the 5 amp current source in this resistor, it's got the same current. So this is 5 volts. So I guess my math estimate wasn't too bad. And you know this is 5 amps. Okay, from this point I have a couple of choices. One choice is I could realize that I have in this node 5 amps coming in and basically minus 0.55 coming out, so 0.55 coming in, which would mean I could calculate the current through this 2 ohm resistor. Or I could take this voltage from here to here, realizing that that's 11 volts, and I could calculate the current that way. Either way, I'll get current directed from left to right, and it'll be 5.5 amps. Okay, and then finally, the voltage from here to here is minus 13.2 volts. So that means the current is minus 13.2 over 3. I also know the voltage across this current source, it's V3, 13.2 volts. And I know the voltage across this current source is 2.8. So I could, at this point, find the power in the sources as well as the current and voltage and power in all the resistors. So that's how you use the node voltage method in a very simple circuit where you have current sources only. I want to talk briefly about how one might use Kramer's rule, but I think I won't do it in this lecture right now. I just really want you to focus on understanding what we're doing with the node equations. So now let's do another one. In this case, we'll put a voltage source in here. And we'll just illustrate how we might work one of these with a voltage source. And once again, we'll choose really simple numbers that are easy to read and easy to track. Let's call this, we'll call it 5 amps. Okay, so once again, the first thing we do is we identify the nodes. In this case, I have 4. So I have 1 at the bottom. This one on the top right takes up the entire top right. So I have 4 nodes. I'll choose a reference. Now when you have a voltage source, it slightly changes the smart way to choose a reference in node voltage. So I'm going to choose my reference here at the bottom, and then I'll label this V1, V2, V3. V1 is what your textbook author would refer to as a non-essential node, because by inspection you know that V1 is 4 volts. But I like to see you go ahead and label the node and write down this particular equation. I think beginners, that's a little easier. Now we're going to need 2 node equations. We need one at V2 and one at V3. So at V2, and let me point out once again very specifically, we do not at this point need to write a node equation at V1. So we already know V1. The only time we would need a node equation at V1 ever in a situation like this is if we wanted the current through the voltage source and it wasn't in series with anything. Then we would need to go back after we solve the circuit and have all the node voltages and figure out what the current is. But in this particular case, that's not going to be necessary. So at V2, we have V2 minus V1 over 3. We have V2 over 2. And we have V2 minus V3 over 1. You probably already noticed that V1 here is 4 volts, and you could have written that directly if you didn't want to write V1. Once again, I think for beginners, it's maybe easier to go ahead and keep track of all your unknowns initially, but I'll leave that up to you. Okay, and then finally we write an equation at node V3. So we have V3 minus V2 over 1. We have 5 amps entering the node, and we have V3 minus 0 over 4. Okay, so those are my 3 equations and 3 unknowns. In this particular case, I won't solve because trying to get as many examples done as possible. Alright, I'm going to pause the video here, and the future examples will make a follow-on video so that you can take a break if you need.